Alright, video number 2. So, as I mentioned in the last video, this is going to be about changing measure. In particular, first I'm going to show moving from P to QD, which is just going to be basically confirming or proving that. And as I showed, we'll get something, we should completely confirm this again. But then also importantly, we're going to move from QD to QF and find out what that is. Those will be important when we derive the solution. In particular, we'll need the solution of those SDEs when we eventually solve the PDE using the Feynman-Cach formula. So let's get started first with P, moving from P to QD. Now when I say P, moving from P, which process am I talking about? It's going to be that, remember Garman Kohlhagen, we always need to be in the domestic currency, so we're basically going to forget about that raw foreign bank account and work with the dynamics of the foreign bank account in domestic currency. And if you recall from the last video, that ended up being alpha plus RF dt plus sigma, times the tilde value itself, dt plus sigma b tilde f dwt. So what we're going to do is we're going to consider this process, but with now BD, the domestic bank account, as the numeraire, and so the D will get moved out. Let me not confuse too much there. Let me leave that like that and say that what we want now, so in this, we're going to move from this to that. Now, to do that, we need to remember the Ito quotient rule, which is that d of x over y is going to be equal to x over y times dx over x minus dy over y minus the cross, and then finally plus dy over y squared. Now, you can prove this to yourself more rigorously, but just you can see that these are going to simply cancel y. Well, remember that the Ito multiplication rules that any dt squared terms are 0, any cross terms are likewise 0, and just if you have a dw squared term, does that become a dt. Now, for the cross terms, we're going to have, this process times the dynamics of the domestic bank account, which you might recall are simply RD times BD. So you're not going to have any dw squared terms. And then likewise for this one, basically you can think of, just think of the numerator. It's kind of this thing foiled. So again, you're not going to have any dw squared terms. So again, you can prove that to yourself more rigorously, but just trust me that they both just cancel out. And then also, let's think about moving this term in. So again, we basically just have that. So what we're going to have is dx over y is equal to x dx over yx, but those cancel, and then you get minus dy. Or I could x over y squared times dy. So this will be kind of the formula that I move with. It's nice to know this by hand. So again, if I'm dealing with something like this where I know that, say, these are going to cancel, I sort of have this kind of memorized by hand. So what I would normally be able to do is to just say, okay, I know I need to, sorry, not that one, this one, do this. And so it's nice to get in the habit of being able to quickly just say, okay, I know that I need to take d over b dt, and that's just simply going to be d bf over b t minus b tilde f t over squared d b d t. So that's what we're working with here. And so that, again, we know d b tilde, and we also obviously know dbt. So this is going to be equal to, let's write this out. So we'll have b tilde. So remember d, what is db tilde f? It's that times alpha plus this r f dt, and I'm gonna, this would all be over b dt, but I'm just gonna put it over just that term. And then you would have minus b tilde f over bd squared, and then times rd bd t dt. So that cancels with one of those. So this is the same as oh, you know what? Wow. This needs something else, doesn't it? That needs a plus sigma. Sorry, not that. Sorry about that. Hope that's not too confusing or muddled. But anyways, now I'm going to gather like terms. So here we basically have a b tilde f rd dt. So we have something that could get included here. And then we're going to have this dwt term by itself. But in doing that, we then end up with b tilde f t. Again, I'm going to keep it over bd t for just that term. But then we'll have alpha plus r f minus r d dt, and then plus b tilde f bd sigma dwt. All right. Now, So this is the differential of this worked out. So now it's important to, we're going to invoke the Girsanov theorem. Now the Girsanov theorem is, obviously a whole complex topic, but we're just going to use the very important result that we can say that that the differential of this Wiener process can be rewritten as some phi d, I'm denoting it subscript d, plus w q d t. So what we're going to do is to basically substitute this in here. So we're going to have d, sorry. So that is equal to, we have tilde f over d alpha plus rf minus rd dt plus alright, so now, and then we'll have sigma, and so now again we're going to fill in that result. So we'll have phi d dt plus, sorry, that's a differential there, dw q d. Alright, so now as we normally do, we're going to gather like terms. So you see that we have this dt term here, and so we can obviously include this, given that, in with these terms, and then we'll again still have then a standalone dw term. So anyways, in the end, after doing that, we will have that the differential of this process under QD is equal to times alpha plus RF minus RD, and then plus, again we have this over here, so it's sigma phi d dt, and then finally plus that term that remains, sigma dw q dt. Fantastic timing for my neighbors to start doing their bathroom remodeling, huh? Anyways, alright, so what do we know? Well, we want a QD martingale, right? So this drift term should equal 0 for a QD martingale. So let's work through that. So alpha plus RF minus RD plus sigma phi D should be equal to 0. So we'll have sigma phi D equals RD minus RF minus alpha over sigma. Sorry, not over sigma. I got a little ahead of myself there. So finally, phi equals RD minus RF minus alpha over sigma. So that is our Girsanov kernel. So finally, what do you do with that? Well, you go back to the original dynamics, that being this, the foreign bank account in domestic currency, and you basically invoke this kernel. So you'll have that D, or sorry, we're not going back to that. We're going back to the raw exchange rate dynamics, sorry. So what we're trying to do is find the exchange rate dynamics under QD. So ignore what I just said. We're going to go back to the exchange rate under P, which if you recall is alpha x t dt plus sigma x t dwt. So we can denote that as p. So going back to this, but invoking Girsanov along with this derived kernel, we have that equals alpha x t dt plus sigma x t. And again, the idea that you can write this as something like this, but we know now what this kernel is, so we're going to fill that in. So we'll have rd minus rf minus alpha over sigma dt plus dwq w under qd at t. Alright, so simplifying this, combining our like terms, we're going to get that dx equals, so we'll have, let's see here. So first note that you can say that this sigma cancels with this here. So we're just going to have alpha plus rd minus rf minus alpha x t dt plus sigma x t dw q d t. Obviously these cancel, you're just left with this. So finally in the end, it'll be equals rd minus rf x t dt plus sigma x t dw q d. Alright, so what do you know? So we got what we wanted, right? So we proved that under qd, that our drift then is equal to rd minus rf, which again matches with our PDE. We already found that. And I already kind of told you, knowing what it is, basically we just proved this result, that under QD, your drift is equal to the domestic minus the foreign rate, and then plus some, QD Wiener process. All right, so that one's important to have, again, even though we already knew it. But now, importantly, we also want to move from QD to QF, because the way we're going to solve the PDE, we're also going to need that. I mean, in particular, we'll need the solution to that SDE, which we'll do in the next video. But nevertheless, we do need this for the way that we're going to derive the solution. So we know we just figured out dx under qd, and we also know, I'll just write it here so you don't have to go back, the dynamics of that foreign bank account in domestic currency was alpha plus rf d, sorry, I keep forgetting that for some reason, b tilde f dt plus sigma x. Wow. Come on, man. All right, so now, just like in Black-Scholes, when we wanted to move from what I called Q to QS, I considered a flipped process. So instead of S over B, it was B over S. So same idea here. We're going to consider the flipped process and find D of BD over B tilde F instead. So the inverse of what we just did. And so, again, following the Ito quotient rule, this is going to be equal to BD over B tilde F times D BD T over B tilde F minus Now, again, here the cross terms are going to fall out, which should be obvious. Unfortunately, I want to go back. I think I said something just completely wrong earlier. I was talking about this term, and I think I mentioned, I was referring to this term, and I said if you FOIL this, nothing's going to happen, which is clearly wrong. You would have a dt term. I was totally mistaking y as this process, when y is just this process, which itself was wrong. Anyways, obviously when you square this process, you're going to have nothing, because all you're going to have is a dt squared term. So this process cancels out, not because this FOILs to nothing, it clearly doesn't, but because this process squared only has a dt squared term. This process cancels because you're not going to have any dwt squared terms either, you'll just have cross terms. Alright, very sorry about that. I realize it here because I'm trying to quickly tell you how some of this stuff will cancel. So likewise here, the cross terms are going to cancel because again, you're just going to have cross terms, so dt, dwt. But in this case, your y process is now this. So this think about FOILing that term. You are going to have a term, a dt term, because this dw term is going to get squared. So I am going to write, I'm going to keep it general for right now, but you will have that over the same thing, squared. All right. So let's start filling some of this in. Yes, yes, yes. Okay. So we're going to have d dt over is equal to b dt over times, and then the differential of the domestic bank account is just rd e over that. Yes, 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 yes. Okay, and then minus I'm sorry, that's not correct. A lot of mistakes in this one. It's unfortunate, but I'm too deep into it now, so that's going to cancel, and then we'll have again yes, yes, yes. That the differential of this is RF. Sorry about that. So those cancel. So I have room. Let me write the final term down here. And then you're going to have, again, sort of the same idea. So you'll have alpha plus RF dt plus sigma b tilde f dwt over. So again, these will cancel, but it's going to be squared. All right, so what do you have? So you will have d is equal to domestic over foreign and domestic. So this term here has just become rd dt. This term here, so it's important to be careful of that minus there. So you're going to have minus alpha plus RF dt minus sigma dwt, and now this term here. So if we think about, so these b tildes dropped out, so you can just think about this numerator without these. So now thinking of the Ito product rule, or multiplication rule, if we think about foiling this, this is going to drop out, the cross terms will drop out, and we're just going to be left with this, which is just going to become sigma squared, and then the dw squared term again becomes a dt. So now let's gather like terms. So our dt's, so we're going to have that this is db, write that a little better. Is equal to bd over b tilde f times, write it like that, rd minus rf minus alpha, and then plus sigma squared dt minus sigma. Use the bracket. All right, so now again we'll invoke the Girsanov result that we can write our dwt term as this time. It's always, phi plus dw, but I'm gonna, subscript the phi with f, just to denote that now we're moving to f, and then plus dwqf. So filling that in, we have differential of bd over b tilde f is equal to bd over b tilde f times rd minus rf minus alpha plus sigma squared dt minus sigma, and then again we fill in this result that it's phi f dt plus dwqf t. All right, so now again gather our terms. So we'll have that d to times RD minus RF minus alpha plus sigma squared. And now here we have this, so it's minus sigma phi f dt minus sigma, and now we have our qf Wiener increment. Okay, now as before, again, we want this drift here to be 0 for a qf martingale. So let's work through that. We'll have RD minus RF minus alpha plus sigma squared minus sigma phi f equals 0. Okay. So this is like saying that negative sigma phi f is equal to, you could say alpha plus RF minus RD minus sigma squared. So if we divide everything by our negative sigma, we're finally going to get that our phi f Girsanov kernel is equal to RD minus RF minus alpha plus sigma squared over sigma. So this is our Girsanov kernel. Now, again, we are moving, that's sigma squared. Now, you saw in the first part, what did we do when we found the phi d Girsanov kernel? We then went back to the p dynamics of x, and invoked that result. So we're going to do something similar now. So we have this phi f Girsanov kernel. We need to plug that into something. But importantly, remember that now we're moving from qd to qf. So we're not going to go back to the... Or sorry, we are. God, that'll have to get edited. So we have our phi f Girsanov kernel now, and so what do we do now? Well, we saw before that when you have this kernel, you basically go back to the original dynamics, and you plug them in. So again, our original dynamics are alpha x for the underlying process, that is, when I talk about original dynamics. dt plus sigma x t dwt. But now we are again going to change this, invoking our result here. So we'll have that dxt equals alpha xt dt plus sigma x t, and then invoke Girsanov with our derived kernel. So rd minus rf minus alpha plus sigma squared. Yes, over sigma. Okay. And then dt plus, and then you have your, but now qf. So with that, we will simplify everything and finally get that dx is equal to, obviously again this cancels with this one, so we just get alpha plus rd minus rf minus alpha plus sigma squared x t dt plus sigma x t, and then we have our new QF increment. So clearly these cancel, and then so finally we're just left with dx t equals rd minus rf plus sigma squared dwqf t. All right, so these are the QF dynamics, and as you can see here, this is basically analogous to in Black-Scholes when we move from Q, or when we move to it was the QS dynamics. The drift basically ended up being r plus sigma squared. So totally analogous to that. Obviously, here under Q, we don't just have r because we have two rates. We have rd minus rf, but then it's the same idea. When moving to QF, we add this sigma squared, just like when we moved to QS, we added a sigma squared. So anyways, it's those are two important SDEs, and I'll write the just to have it, I'll write the QD dynamics. Same idea, again, just without that sigma squared. So in the next video, we will solve both of these SDEs, because those solutions we will, when I mean solve, I mean we're going to find what xt is, because we'll need both of those solutions for when we, in the fourth video, solve the PDE with Feynman-Cach to get the solution for a European foreign exchange call option.